this video, we're going to follow up on the last video discussing how to calculate and use z-scores and give you four different kind of work problems. First, I just want to review quickly what a z-score is. A z-score is a linear transformation of one measurement to another measurement. We're going to go from one scale to another. Our original scale might be something like how old you are in years, so your age in years, and the output variable will be how old you are in z-score units. When I say this is a linear transformation, we're really not changing any of the numerical information contained in the variable. We're simply converting it to a different scale. It's very similar to comparing temperature in centigrade to temperature in Fahrenheit. They're still both measuring temperature. It's still the same temperature outside, just in one scale it's expressed in centigrade, in another in Fahrenheit. The primary outcome of this operation is to create a new variable that has a mean of 0 and a standard deviation of 1. So here's this slide we saw before. There are three different distributions. They have different means and different standard deviations, and when converted to z-scores, they all have the same mean and the same standard deviation. That allows us to compare these three different distributions in one step looking at z-scores. Here's another example. This is using 2010 data from the General Social Survey. The graphic on the left is a frequency distribution and a histogram of age for all the respondents. It's not a very pretty graphic, but you get the idea. We have the ages along the x-axis, and we have the percentage of people in each age group on the y-axis. On the right-hand side of the graphic, I've duplicated the same graph by creating a new variable, which is the z-score of age. And on the x-axis, instead of having age, we have z-score. And on the y-axis, we still have percentage. And lo and behold, there's no difference in these two graphics. That is, the information contained in the original age variable is identical to the information contained in the new z-score variable, except that the values on the x-axis in the one hand is measured in years of age, and in the other is in z-score units of age. Let's start working some of these problems. We're going to do four different kinds of problems. Problem number one is a class of problems that I call bounded by the mean, and that's a straight z-table lookup. So you're going to need the z-table in the back of the book. Problem number two is an example where the mean is in the middle of an area that we're interested in. This is an addition problem. Problem number three, the mean is going to be outside of the area that we're interested in, and that's a subtraction problem. And then the fourth kind of problem is solving for a percentile. This is a made-up example, but it'll give you an idea of how to work z-score problems. So let's assume that we've given an English placement test to incoming students at a university, 900 students coming in. We know that the distribution of examination scores is approximately normal, has a mean of 82, and a standard deviation of 5. We're going to use this information to estimate how many students had test scores between 82 and 90. In doing these kinds of problems, the first thing I like to do is to graph my normal distribution out and label all the areas with the information that I have in front of me. You can see here that I've drawn a vertical bar at 82, and I've shaded in the area up to 90. We're interested in that particular area because we know that area under a curve is a proportion and can also be used as a probability. If I know the proportion of people that had test scores between 82 and 90, I could multiply that by the number of people who took the exam, 900, to get an approximation of the number of people with scores between 82 and 90. Notice that I have two scales here. The first scale is in test scores, the 82 and the 90. And underneath it, I've put down what I know about the z-scores. I know that a score equal to the mean has a z-score of 0. I don't know what a score equal to 90 has for a z-score. I have to calculate that. So here's what we're going to do. We're going to convert the examination score to a z-score. We're going to look up the z-scores in a normal table, and we're going to find the associated area and then determine what the probability is of having students who scored between 82 and 90. In the first z-score, you can see that 82 minus 82 divided by 5 is equal to 0. That is, the test score minus 82 divided by 5 is equal to 0. Right? That's pretty obvious, so we know that when we have a score right at the mean, which is a boundary in this problem, then the z-score has to be equal to 0. I didn't really have to calculate that z-score, but I did it just to show you what the outcome is. The more important z-score is the one for a score of 90. So here I take my test score of 90 minus the mean of 82, divide by 5, and I get a z-score of 1.6. Now you can see in the graphic here I've labeled the things that I know. I know that half the distribution has values below 82, so I've labeled that 0.5000. By going to the z-table in the book, I learned that the area between a mean of 0 and a z-score of 1.6 is 0.4452. And I put that in, that's the blackened or darkened area. So the probability of being between, having scores between 82 and 90 is 0.4452. Either using the table or doing subtraction, 0.5 minus 0.4452, I've also labeled the area in the tail, the smaller white area to the right, as 0.0548. I didn't really need that piece of information, but I just labeled it to show you that these three areas sum up to 1. So now I can go ahead and solve for the number of students. 900 students times the probability of being in the range of 82 to 90 leads me to learn that there are approximately 401 students that had scores in this range of values. This is a straight table lookup, and by that I mean I really only had to calculate the z-score for people with scores of 90, enter the z-table with the 1.6 value for the z-score, look up the 0.4452, do the multiplication, and I'm done. This example is a little bit different. So we have the same English placement exam, same mean, same standard deviation, but now I'm interested in how many students had test scores between 75 and 85. When I graph that out to see what my problem looks like and what information I know, you can see that the vertical red bar that represents the mean of 82 falls in the middle of this range of values. It falls between 75 and 85. So the process for solving this problem now is like the first one. I need to find the area or the probability of that black area, the dark area. And I'm going to do this by solving for two z-scores, one for 75, and figuring out what area lies between 82 and 75, the mean in 75. And then I'm going to calculate the z-score for 85 and use the z-table to find out what area of that distribution lies between 82 and 85. And I'm going to add those two areas together. So here's the work. Step 1, convert the examination scores to z-scores. Z sub 75 is equal to 75 minus 82 divided by 5. And I get a z-score of 1.4. Notice that I didn't put the minus sign in here. Technically, it's minus 1.4, but my z-table only has positive values, so I just left it as positive, and I'll remember that it's below the mean. My z-score associated with a raw score of 85 is equal to 85 minus 82 divided by 5, or 0.6. So I'm interested now in getting the probability of the area between minus 1.4 and 0.6, or in another metric, 75 and 85. I've entered the probabilities here in this graphic based on the data I got out of the z-table. I used the z-table to discover that in the lower tail, the white area to the left, there's 0.0808 of the distribution. Between 75 and 82, I have 0.4192 of the distribution. Between 82 and 85, I have 0.2257 of the distribution, and then in the white area to the right, I have 0.2743. Those four numbers sum to 1, or the entire area under the curve. Now it's pretty easy just to add those two areas together for the blackened area, and I find that from 75 to 85 lies approximately 0.6449 of the distribution. And like the problem before, I'll multiply that probability times 900 and discover that approximately 580 students fell or had scores between 75 and 85. This is an addition problem because the mean of the distribution, the mean of the data, lies between the two values that we're interested in. 82 lies between 75 and 85. Here's our third problem. Just like the last ones, but now I'm interested in how many students had test scores between 90 and 95. When I draw this to see and lay out the information that I have, you can see here that the vertical red line, which represents the mean of 82, falls outside the interval I'm interested in. Obviously, 82 doesn't lie between 90 and 95. This is going to be a little bit different kind of problem. We're going to have to do some subtraction. The way we're going to do this, again, is based on the same principles we've already used. We're going to convert the score of 90 to a z-score and look up the area for that between the mean of 82 and a mean of 90. We're going to convert the 95 to a z-score and use the z-table to get the area between a mean of 82 and a mean of 95. And then we're going to subtract that area from the other area to get that little piece that's shaded in, which is the proportion or probability of students who had scores between 90 and 95. And again, we'll multiply that by 900 to get an approximation of the number of students in that shaded in area. So step number one, let's convert both of those scores to z-scores. Again, if you look at that z sub 90, that's a positive number, and the z sub 95, that's a positive number as well. 90 minus 82 divided by 5 is a z-score of 1.6. 95 minus 82 divided by 5 is a z-score equal to 2.6. Entering the z-table, I discovered that between value of 82 and 95, there's approximately 0.4953 of the distribution. And between a score of 82 and 90, there's approximately 0.4452 of the distribution. The difference between those two areas is 0.0501 and represents the area in the shaded section of that distribution. And of course, that's a probability. So for example, if I were to draw a student out at random out of those 900 students, the probability that that student had a score between 90 and 95 would be 0.0501. Here I'm subtracting the areas to get to that 0.0501, and that's why I call this a subtraction problem. If I multiply that probability or that proportion by 900, we find out that we would expect approximately 45 students to be in this region of the distribution. This is a subtraction problem, or anytime you see a mean that is not in the area of interest, you can treat it as a subtraction problem. Calculate the two z-scores, look up the two areas, calculate the difference to get the area that's common to both of them. Last problem we'll go through is a percentile problem. Here we're asking the question, what score is equal to p sub 92, or the 92nd percentile? So graphing this out to see what I know, that red line on the right represents the 92nd percentile. I know that the 92nd percentile is the location in a distribution that divides the distribution into two pieces. The piece to the left or below that value has to be 0.92, because 92nd percentile means that 92% of all the cases had values at or below whatever value this is. And if 0.92 lies below, then obviously 0.08 must lie above. Notice that I've put down there p sub 92 equals question mark. That's the problem. How do we figure out what the test score is equal to the 92nd percentile? So I'm going to use the z-table now a little bit differently. I know in this graphic you can see I've laid out all three regions of my normal distribution. There's 0.5 below the mean. There's 0.42 between the mean and the 92nd percentile, whatever that number is, and there's 0.08 above. Going to the z-table, I go inside the z-table. I don't look at the z-scores. I look at the areas between the mean and z, and I'm looking for the value of 0.42. If I can find 0.42, then I just have to read to the side of the table to get the exact z-score associated with that particular location in the distribution. Now, this is a little bit of a problem because you can see that 0.42, when you go to your table, your z-table, doesn't exist in the table. I can find 0.4192. I can find 0.4207, the values that are right around 0.42, but I can't find 0.42 itself. If you may have learned in middle school or high school how to interpolate numbers, and more technically we should probably interpolate this, but the amount of error is so small that my suggestion for this course is simply take the closest value, which in this case is a z-score of 1.41. So now we know that the score at the 92nd percentile is a z-score of 1.41. But that's not very illuminating since most of us don't think in terms of z-scores. I need to take that z-score and convert it back to the original metric, which is a test score. And that's pretty simple to do. We know that our formula for the z-score is y minus y bar divided by the standard deviation of y. And if I manipulate this algebraically, I can solve for y. And I get y equals zs plus y bar. Now it's a simple problem of just substituting in those numbers. My raw score, or my test score, is going to be equal to the z-score I looked up in the table, 1.41, times the standard deviation, plus the mean of the test scores. And I find out that the 92nd percentile is equal to 89.05, meaning for people that have scores of 89.05, their score was equal to or greater than 92% of the people who took the test. And alternatively, it means that 8% of the people who took the test scored higher than them. You can see that in this z-score formula, there are 4 pieces of information: z, y, y bar, and s. And therefore, if you know any of 3 pieces of information, you can solve for the 4th. So don't be surprised if on a test or a quiz, we don't ask you to solve for y, but we ask you to solve for the standard deviation or some other value. It really doesn't matter as long as you know that if you know 3 pieces of information, you can algebraically solve and then plug in the 3 pieces of information you know into your formula and solve for the last piece of information. Z-scores have a lot of uses in statistics. Hopefully these 4 problems give you a little insight into how to use them and a little bit of practice at using the z-score table. Thanks for watching the video, and we'll see you in class.